Hello, everyone. Today, we will continue studying the three mechanical states of polymers and their two transitions. First, let's take a look at the teaching objectives of this section. The first is the ability objective, to be able to explain the characteristics of the transitions among the three mechanical states of polymers. The second is the knowledge objective, to understand the relationship among the three mechanical states, the two transitions, and the characteristic temperatures. The third is the quality objective, to cultivate interest in learning and motivation, a rigorous academic spirit, and a constantly progressive scientific attitude. Mechanical state refers to the state of existence of a material defined by its mechanical properties. Mechanical state transition refers to the change in the state of existence caused by variations in the material's mechanical properties under an external field, mainly temperature. Each mechanical state is associated with a specific molecular motion mode. Therefore, a change in the mechanical state reflects the dependence of molecular motion on the external field, temperature. This dependence is macroscopically manifested in the mechanical properties. Polymers have three mechanical states, which means there must be two intermediate transition regions, from the glassy state to the rubbery state, and from the rubbery state to the viscous flow state. These two transition regions are referred to as the two transitions, and the corresponding temperatures are called the corresponding transition temperatures. First, let's look at the glass transition and the glass transition temperature. The so-called glass transition is the transition between the glassy state and the rubbery state. It can be from the glassy state to the rubbery state or from the rubbery state to the glassy state. This is the first transition, called the glass transition, and the corresponding temperature is called the glass transition temperature. Since the glass transition temperature is an important physical parameter, it has been given a special symbol in polymer science, called Tg. The glass transition temperature is denoted as Tg. The other is the viscous flow transition and its characteristic temperature, Tf. The so-called viscous flow transition refers to the transition between the rubbery state and the viscous flow state, and the corresponding temperature is called the viscous flow temperature. Our textbooks rarely mention the viscous flow transition, so just be aware of it. Next are the four characteristic temperatures. First, let's look at the temperature deformation curve characteristics of amorphous polymers. First, deformation changes with temperature. Second, polymers exhibit three mechanical states: the glassy state, the rubbery state, and the viscous flow state. There are two transitions. The transition between the glassy state and the rubbery state is called the glass transition, and the transition between the rubbery state and the viscous flow state is called the viscous flow transition. The four characteristic temperatures correspond to the brittleness temperature, the glass transition temperature, the viscous flow temperature, and the thermal decomposition temperature. In a more detailed temperature deformation curve, it should look like this. The far left end of the curve is our brittleness temperature. Above the brittleness temperature is the glassy state. As the temperature continues to rise, in the transition region appears Tg, the glass transition temperature. As the temperature continues to rise, we reach the rubbery state. The temperature of the rubbery state continues to rise. After the second transition, that is, the viscous flow transition, there is a temperature called the viscous flow temperature. Above the viscous flow temperature is the viscous flow state. When the temperature rises to a certain extent, the polymer will undergo thermal decomposition. The brittleness temperature refers to the temperature at which a plastic material becomes brittle under impact load. Generally, the temperature at which 50% of the samples undergo brittle failure under specified impact conditions is defined as the brittleness temperature, represented by the symbol Tb. The brittleness temperature is the lower limit of the temperature at which plastic materials can be normally used. especially in many areas where the flexibility of soft plastics is needed, below the brittleness temperature. plastics lose their flexibility, become brittle and fragile, and cannot be used normally. TG, the glass transition temperature, is the transition temperature between the glassy state and the rubbery state, also known as the glass transition temperature. The glass transition temperature is an important parameter, and we will continue to explain it to you in subsequent courses. The viscous flow temperature TF is the transition temperature between the rubbery state and the viscous flow state. The thermal decomposition temperature is the temperature at which polymer materials begin to undergo chemical changes such as cross-linking and degradation. The thermal decomposition temperature is generally represented by TD. TD is the temperature that polymer forming and processing cannot exceed. Usually, the processing range of the viscous flow state is between the viscous flow temperature and the thermal decomposition temperature. Next, let's explore the effect of molecular weight on the glass transition temperature. First, let's look at the first part, the relationship between the glass transition temperature and the molecular weight. What is the motion unit corresponding to the glass transition? It is the chain segment. When the temperature rises above Tg, the motion of the chain segment begins. The larger the molecular weight, the more chain segments there are. Polymers with smaller molecular weights have fewer chain segments, while those with larger molecular weights have more chain segments. Molecular weight does affect it, but the effect is very small. That is, within the range of typical polymers, it is hardly affected by molecular weight. Although the effect is weak, there is still a slight influence. The higher the average relative molecular weight of the polymer, the higher the Tg. However, when the average relative molecular weight increases to a certain extent, the glass transition temperature tends to a certain value. Next, let's look at the second part, the relationship between the viscous flow transition temperature, TF, and the molecular weight. What is the motion unit corresponding to the viscous flow transition? It is the entire macromolecular chain, which moves as a whole and becomes larger with increasing molecular weight. The molecular weight increases, so a larger activation energy and greater free volume are needed to make the molecular chain move. Therefore, the viscous flow temperature rises sharply with the increase of molecular weight. The relationship between the viscous flow temperature and the molecular weight is strongly correlated. It rises sharply with the increase of molecular weight. The different dependencies of the glass transition temperature and the viscous flow temperature on the molecular weight are due to the different sizes of the motion units corresponding to these two transition temperatures. For the same polymer with different molecular weights, assuming M2 is greater than M1. Now let's draw the temperature deformation curves corresponding to the two molecular weights. We can get the curve shown in the figure. When its molecular weight increases, as we just said, the glass transition temperature, Tg, does not change significantly with the molecular weight, and the dependence is relatively small. It hardly changes, so its glass transition region is still basically the same. However, the viscous flow temperature Tf increases with the increase of molecular weight, so Tf moves to the right. And the viscous flow transition region also moves to the right accordingly. In summary, the position of Tg remains unchanged, and Tf increases. Therefore, the temperature range of the rubbery state becomes wider. When the molecular weight increases, the temperature range of the rubbery state of the polymer becomes wider, becoming the curve on the right. This is the effect of molecular weight on the temperature deformation curve. This section of the course ends here. Everyone, see you in the next class.